Hello. Thanks. Well, he's gone. Thanks, Robert, for the introduction. I'm just waiting for my presentation. Yeah, there we go. OK, ready to go. So thank you all for having me. It's really a pleasure to be here. I want to take this time today to rethink with you together the role that robots can have in construction. Construction today faces existential challenges. It generates immense amounts of emissions and waste. It faces a labor shortage due to precarious job conditions. And we're witnessing an urgent need to house many people. This might lead us to believe that we can employ robots the way that we see them being used in other industries, such as manufacturing, to solve these problems by automating the manual labor and basically replacing humans. However, the challenges that we face are very different from those of other industries. Construction sites are messy, they're complex, they're really hard to control, they're constantly changing. We experience more and more the need to work with materials that are imperfect, such as reclaimed elements, less processed materials that are, again, difficult to control. And if we want to really address the labor shortage issue, instead of pushing humans out of the market by replacing them with humans, we should think about making construction as a job more accessible and more valuable to a larger range of the population. So I see my role here really to rethink the roles that humans and machines have in construction, in pursuit of processes that move away from automation as we know it, and instead towards collaboration. I run the lab for Creative Computation, CRCL, we call ourselves, and I'd like to take the next few minutes to share with you our vision and our workflow from the way that we imagine and we adapt the robots that we use to the specific material applications that we implement. So we typically work with industrial robots, mainly because of their versatility and their robustness. They're big machines, they're heavy, they can really be employed in construction, but they're not very smart machines. So we use them more as a canvas and to make them fit our needs. And we think about processes in which machines and humans can take over different roles. Such as here, where two robots alternate the placement of bricks while the humans do the connections, and this way we are able to build arches and vaults without the need of any support structures. Now, this is a very typical role division that we see in construction, where we use robots to take over tasks that are difficult for humans, such as holding heavy bricks or structures in mid-air for long times, or placing things precisely. And humans are used to perform the more dexterous actions, like placing the glue for the connections in this case. We plan these processes precisely from the design to the structural stability, up to each individual robotic instruction, and monitoring inaccuracies and problems that we might encounter along the way. And in this case, for example, we built this vault using perfectly shaped, expensive, really beautiful but really expensive glass bricks in order to get this perfectly aligned vault. Now, what if we don't have these perfect conditions and these perfect materials? I talked about the amount of waste that construction produces. So what if we focus on building with what is left, with materials that are anything but perfect, that are irregular, brittle, and not known to us before we start construction? Now, one way of tackling this is by increasing the robot's autonomy. So to build structures similar to what I've shown before, we do this by teaching the robot how to decide what to do instead of telling it exactly what to do. So if we look at this example of the arch, we defined a problem by telling the algorithm we want to span from one support to the other, but at no point in the process did we tell the algorithm that we want to build an arch and that this is what the arch should look like. We do this by using reinforcement learning and by training a policy that is capable of addressing multiple goals. And that way, at every step, really, the model decides where to place the next block, what makes sense, while taking into account structural stability and the robotic constraints that we have. And we don't just do this in simulation. Instead, we apply it in the physical world. So during construction, at every step, we scan where we are and what we built. And this is used as an input for the next step, so that decisions about every step are based on the reality that we see. And this is really crucial for construction because we have a lot of reasons for inaccuracies, for imprecisions, and this is really the target, what we want to achieve. We want to be able to react to it. So the way that it looks in reality, and you might see these are not the big, beautiful arches that I've shown. We had to scale down a little bit to start solving the problem. But we set up the problem with a target and obstacles, and then at every step, the robot decides where to place a block. We scan it in, we feed that as the new input, and it continues taking decisions until we solve the problem that we give it. Now, a different approach that we use to tackle this problem of imprecise materials, uncertainties that we encounter, is through interactive construction. Instead of focusing, again, on standardized, new, processed wood, we do a lot of work on working with offcuts and with materials that are salvaged from deconstruction sites. In this case, we use an interface that uses projections to enable us to change the design during construction, right on the construction floor. And we do this in order to be able to fit these materials that aren't perfect, instead of requiring a perfect plan of where to place each of them. So we don't need to have the knowledge about every single piece of wood before we start building. What we want to do is to achieve the types of interactions that we typically see in traditional construction sites, where workers are really good at making things fit and making up for things that aren't perfect. And we want to bring that back into the robotic processes. So the way that this looks like is we have an initial design that we work with. We have this projections interface, and we are really able to intervene onto the construction floor to make changes to the design, to introduce new elements, to move nodes around, and to decide where each piece goes. And then the entire process of processing, cutting the pieces, and placing them in the target location is automated. Everything is generated on the fly, the robotic path to get the piece into its final position happens there. And this allows us, again, to react while we build. The whole goal that we have is to not rely on these perfect plans from the very beginning, but to be able to intervene and to adapt, to stop us from having to go back all the time if something doesn't go right. Another material that we look at is concrete. Concrete is really particularly challenging as it comes in large, heavy pieces from demolition sites. So what we do here, this is a collaboration with the SXL lab here at EPFL as well. We look at using concrete in this initial state as it comes from demolition sites, without further processing it down to maintain its value as much as possible. And we do so by searching for configurations that are stable, that follow masonry rules, which we know provide optimal stability. We scan every piece before we start planning, and then we use packing algorithms to achieve these configurations for the new pieces. And then we stack basically each piece one by one into the desired location. We use cement in between to be able to produce these new walls. Given the weight of concrete pieces, this very quickly exceeds the load and capacity of industrial robots. So instead, we use the robot here to drill attachment points so that we can lift the pieces into the precise position as they are needed for placement. And we moved away from robots. We actually use cranes, with Ganter crane in the lab, but this could be a crane on the construction site, which we then augment with cameras and sensors to be able to control the precise movement and ensure this precise placement. And this leads to us being able to assemble these walls that can be employed as they are in new construction while reducing the environmental impact that we have. Now, finally, we don't just work with material after deconstruction or after demolition. We want to be able to intervene directly on existing structures while they are still standing. And the reason we do this is to be able to make changes required to extend the building's life, rather than saying, okay, we demolish it and we do something new. So the earlier we can get in, the earlier we can change, the more chances we are to keep buildings longer in use. The way that we do this, we have this project on wooden structures. So we digitize the structure that we have. We get it through a 3D scan. And then we compute sequences for its reconfiguration such that we achieve a new spatial layout without having to disassemble the entire structure, to inventory every piece, to have, again, the perfect information about every piece. Instead, we really go step by step. We take the information as it comes, and we make decisions on where to place it. And we use, again, the humans and the robots in collaboration to take over the different tasks that are required. We have robots that we use to cut pieces if it's out of reach for the human. We have situations in which the robot holds the piece and the human cuts. We have the two robots working together. And by going through this sequence, ultimately, we achieve a new configuration for the structure. And I'll show you a little bit what this looks like in the video. Wake up. So to wrap up, I'm really here to envision construction sites in which humans and machines can work together, in which they communicate with each other in order to support each other, really with the purpose of reducing our environmental impact, of making construction more accessible and more enjoyable, and to focus on the needs of the industry, which are really to renovate, to repair, and to extend buildings' lives. And these are most of the people that were involved in the project. Some of them are here today, so please, if you see their faces, talk to them. Join us in this effort. I would love to hear from you and to figure out how we can push this further. Thank you very much. Where do I go?
So, Stefana, I have a question for you.
Yeah, there's questions.
So people found the Slido link, and so now... So one of the audiences, they asked, this is Konstantin Dinev, he's asking, what are your quality control procedures for ensuring recycled materials meeting the structural requirements?
Yeah. So we're really in the initial testing phase and implementation phases of these processes, since all of this is completely new. We think about, and this is a major challenge that we're very aware of what do we need to test to know how we can use the material. We did testing on the wooden structures. We looked at the humidity of the elements that can tell us a lot about the quality of the wood. We looked at the strength of it. We do visual inspections, and we take all this information to make an evaluation of roughly what state the piece is in. But this is a key question that we're working on. We want to automate and to be able to learn a lot more about the material through vision systems, through using learning, and hopefully being able to make quicker decisions and safer decisions for that.
And maybe also other ways besides vision, right? When you have
yes,
piece of wood,
also testing, really, like testing, ideally non-invasive, but if necessary, even invasive testing on a small piece will tell us so much that it's worth cutting a piece off.
And so there's the other question about, in the woodworking video, who was the person assisting whom? Was it both ways? Was it one way or the other? Who was mostly assisting whom, the human, the robot, or vice versa?
I mean, I would say it's really both ways. That's our goal. We use that project really to test all sorts of scenarios that we have. We are now in the process of consolidating and really figuring out, okay, can we make this more structured and who should do what when? But we're interested in both ways. We really had the robot holding the element while the human can cut it or perform a joint or connect it, but we also had the human going in and, like you saw maybe with the hammer, like helping it a little bit if the robotic process wasn't as precise as possible. So both ways should be the way to go. That's the goal.
Thank you. Let's give a hand to Stefana. Thanks a lot.
Thanks so much. Thank you.